Okay, in this lecture, we're going to continue with our section 3.3 material on trigonometric substitution. So last time when we started this section, we mentioned that this method of trig substitution can be used to evaluate integrals that involve the square root of a sum or difference of squares if a u substitution doesn't work. So we saw, depending on what type of expression we have in our integrand, if it's something of the form square root of x squared minus a squared, square root of a squared minus x squared, or the square root of x squared plus a squared, we would make a substitution involving different trig functions in order to simplify our integrand. So in this lecture, we'll look at some more examples of trig substitution and try to recognize when we would use a particular substitution for a given integral. So in our next example, we're asked to evaluate the given integral. We'll look at a few parts, and in part A, we've got the following. And at first glance, it may not appear that this should be a problem involving a trig substitution. But if I think about the denominator of this integrand, 4 minus x squared to the 3 halves, well, we've seen that the 3 halves power of an expression is really the same as the square root of that expression cubed. So here our denominator, 4 minus x squared to the 3 halves, is the same as the square root of 4 minus x squared, quantity cubed. So when we see that our denominator involves a square root of the difference of squares, 4 minus x squared, or 2 squared minus x squared, that suggests that we should try a trig substitution. And for an integrand involving that form, we would make the substitution x is equal to a, or in this case 2, times sine of theta, in which case dx is given by 2 cosine theta d theta, and this square root term, the square root of 4 minus x squared, reduces to 2 cosine theta. So let's take the integral that we had, that is x squared over the square root of 4 minus x squared quantity cubed dx, and rewrite it in terms of theta. So our numerator, x squared, will be 4 sine squared theta, just squaring what we had for x. And then our denominator, well, we said this square root of 4 minus x squared is 2 cosine of theta. And then we're cubing that expression. And on the end, we have a dx, which was 2 cosine of theta d theta. So after we make this substitution, let's simplify a little bit. So grouping some of our constant terms, well, in the numerator, we have a 4 times 2, or 8, with our sine squared theta. And then I'm going to cancel 1 power of cosine theta in the numerator and denominator. Or maybe let me first write it in this form. We had a sine squared theta, cosine theta, d theta. And this was all over 2 cosine of theta cubed, which would be 8 cosine theta cubed. So simplifying a little bit, well, we see that we can cancel this constant factor of 8 on top and bottom, and canceling 1 power of cosine theta, I'm left with the integral of sine squared theta over cosine squared theta d theta, or I can write that as the integral of sine theta over cosine theta quantity squared d theta. But then this term in parentheses, sine over cosine theta, is just tangent theta, and I'm squaring that quantity. So I simplify my integrand down to the integral of tangent squared theta. And in order to handle a trig integral that involves this even or only even powers of tangent, we can make use of the trig identity that tangent squared of theta is equal to secant squared of theta minus 1. And I now know how to find antiderivatives for each of these terms. The antiderivative of secant squared theta is tangent theta, minus the antiderivative of 1 with respect to theta would be 1 theta. And since this was an indefinite integral, I want to include my constant of integration c. Now, as we saw in the first part of this section, we want our final answer to be in terms of the variable x, that is the same variable that we started with. So I need to convert these expressions involving theta back to expressions in terms of x. So to do that, well, there's a few approaches we could use. One approach is to make use of a reference triangle. So let's consider a little scratch work to the side here. If we consider a right triangle formed by this angle theta, well, looking at the substitution that we made, x was equal to 2 sine of theta, or sine of theta is equal to x over 2. And in terms of the sides of a triangle, sine of theta is defined as the opposite over the hypotenuse. So since sine of theta was x over 2, that means our opposite edge is x, the hypotenuse is 2, and then solving for our third edge using the Pythagorean theorem, or what we know about cosine of theta from our substitution, we find this third edge is the square root of 4 minus x squared. So going back to our answer, well, we had tangent of theta, which in terms of the sides of a triangle is defined as opposite over adjacent. So we're going to have x over the square root of 4 minus x squared by looking at our reference triangle, and then minus theta. Now to solve for theta, well, we can use our substitution directly. If we found that sine of theta is x over 2, then theta would be the arcsine of x over 2, plus our constant c. So we would have the following for the antiderivative of this function. All right. So let's look at some other ones. In part B, we have a definite integral from 0 to 3 of dx over the square root of 9 plus x squared. So when I look at this integrand, I see that my denominator involves the square root of a sum of squares, 9 plus x squared or 3 squared plus x squared. So that immediately suggests that I should try a trig substitution. And if my integrand involves the square root of a sum of squares, I'm going to make the substitution x is equal to a, in this case 3, times tangent theta. In which case dx would be 3 secant squared theta d theta. And this expression in the denominator, that is the square root of 9 plus x squared, reduces to 3 secant theta. Now I want to rewrite my integral in terms of theta instead of x, and this is the first example we've seen with a definite integral. So if I make a substitution involving a definite integral, and I'm changing the variable, I need to also change my limits of integration. So let's take a look at how we would find our limits of integration in terms of theta. So looking at the lower limit of integration for the original integral, if x is 0, then substituting 0 into the equation for our substitution, well, we said x is 3 tangent theta. So if x is 0, that means that tangent theta would have to be 0, which means that theta would be 0. And looking at our upper limit of integration, if x is equal to 3, then substituting x equals 3 into the equation for our substitution, we have 3 equals 3 tangent theta, or tangent theta is equal to 1, which implies that theta would be pi over 4. So let's rewrite our original integral in terms of theta. So we now have the integral from 0 to pi over 4. Our numerator was dx, which we said is 3 secant squared theta, d theta. And then we were dividing by the square root of 9 plus x squared, which is 3 secant theta. So of course, one factor of 3 will cancel, and we can cancel 1 power of secant theta, and we're left with the integral from 0 to pi over 4 of secant theta d theta. So thinking back to our section 1.5 material on integration by substitution, well, we derived a formula for the antiderivative of secant theta, which was the natural log of the absolute value of secant theta plus tangent theta. And this is a definite integral, so we're going to take that antiderivative and evaluate from 0 to pi over 4. Now these values, 0 and pi over 4, are theta values, not x values, so I don't want to go back to an answer in terms of x here. I want to plug in these values for theta directly. So let's see what we have here. We've got the natural log of absolute value, secant pi over 4, which would be root 2, plus tangent of pi over 4, which is 1. And then we subtract what we get when we evaluate at 0. So we would have the natural log of the absolute value of secant 0, which is 1, plus tangent of 0, which is 0. So this second term is just the natural log of 1, which is 0. So we're left with just our first expression, the natural log of square root 2 plus 1. And since root 2 plus 1 is a positive number, I don't have to write the absolute value anymore. All right. So we see a little review on a trig substitution, and we see our first example involving a definite integral. So again, anytime we have a definite integral and we're making a substitution, we want to be sure to change our limits of integration to values in terms of the new variable. So let's consider another one. Part C, we have the integral of the square root of x squared minus 81 over x to the 4th dx. So again, as soon as I see that my numerator involves a square root of a difference of squares, x squared minus 81 or x squared minus 9 squared, that should suggest to me that I try a trig substitution. And for an integrand of this form, the substitution that we would make is x equals to a, in this case 9, secant theta, so that dx would be 9 secant theta tangent theta d theta, and the square root of x squared minus 81 would reduce to 9 tangent theta. So let's rewrite our integral in terms of theta. So we have the square root of x squared minus 81 over x to the fourth dx. And we said that our numerator is going to be 9 tangent theta divided by x to the fourth. So that would be 9 secant theta to the fourth power. And then dx was 9 secant theta tangent theta d theta. So let's see what we have here. Combining the terms in our numerator, we have 9 times 9, or 81, secant theta, and then we had 2 factors of tangent theta, d theta. And our denominator was 9 secant theta to the fourth power, so that's 9 to the fourth times secant theta to the fourth. So let's simplify a little bit here. Canceling some constants, well, our numerator, we have an 81, or 9 squared, divided by 9 to the fourth. It's going to leave us with 1 over 9 squared, or 1 over 81, which I can bring out in front of my integral. Then we had a secant theta over secant theta to the fourth. So if I cancel 1 power, I'm left with a secant cubed theta in the denominator. So let's see what we've got. We now have a tangent squared theta over secant cubed theta d theta. So this integrand looks a little messy, and it's involving powers of secant and tangent, but we typically don't prefer to work with the trig functions secant or cosecant or cotangent. It's often helpful to rewrite these things in terms of sine and cosine, which we're a little more familiar with. So let's see what we would have if we rewrite this in terms of sines and cosines. So this tangent squared theta, well, tangent is the same as sine over cosine. So squaring this, we would have sine squared theta over cosine squared theta. And then we were dividing by secant theta cubed. Now secant theta is 1 over cosine of theta. So if we have 1 over secant, that's the same as cosine of theta. So the 1 over secant cubed is the same as cosine cubed. And now we can cancel 2 powers of cosine theta, and we're left with 1 over 81 times the integral of sine squared theta cosine theta d theta. All right. So from here, we can make a u substitution. We have a trig integral involving a product of powers of sine and cosine. We see that cosine is odd, and we've got 1 power of cosine theta factored out. So if I make a substitution of u equals sine theta, then du is cosine theta d theta, and we can rewrite our integral as 1 over 81 times the integral of u squared du. So that would give us 1 over 81 times 1/3 u squared. So that gives us, let's see, 1 over 243 u cubed where u was sine of theta. So we've got sine of theta cubed plus c. And in my last step, I want to get my answer in terms of the variable x instead of theta. So again, to do that, we can make use of a reference triangle. So a little scratch work at the top here. If we consider a right triangle produced by this angle measure theta, looking at our substitution, we said x was 9 secant theta. So in other words, secant theta is x over 9. And in terms of the sides of a triangle, secant is defined as the hypotenuse divided by the adjacent sides. So since secant theta was x over 9, the hypotenuse is x, our adjacent edge is 9, and solving for this third edge, we have the square root of x squared minus 81. So going back to our answer, well, we have 1 over 243 sine of theta cubed. So let's find sine of theta in terms of x using this triangle. So sine is defined in terms of a triangle as opposite over the hypotenuse. So I've got the square root of x squared minus 81 over x. I'm then cubing that quantity, and we've got our plus c. All right, so this would be my antiderivative for that function. So let's look at another one. Here we have the square root of 16 minus x squared, or 4 squared minus x squared. So again, I see that my integrand involves a square root of a difference of squares, which should suggest that we try a trig substitution. And for an integrand of this form, the substitution I would make is x equals 4 sine theta, so that dx would be 4 cosine of theta, d theta, and the square root of 16 minus x squared is then 4 cosine of theta. So making this substitution, let's rewrite our integral in terms of theta. So this square root term was 4 cosine of theta, and then times dx. So we had dx was 4 cosine of theta d theta. So taking the product, we have the integral of 16 cosine squared theta d theta. And to evaluate the antiderivative of cosine squared, since it involves just an even power of cosine, we're going to use our trig identity for cosine squared theta. Namely, that cosine squared is equal to 1 plus cosine of 2 theta all over 2. So we're left with the integral of 8 times 1 plus cosine of 2 theta d theta, which gives us 8 times theta plus 1/2 of sine 2 theta plus c. Now, again, we want to move from an answer involving the variable theta to an answer in terms of x, the same variable that we started with. And what's a little tricky about this example is that our answer involves a sine of 2 theta instead of just trig functions, say involving sine, cosine, tangent, secant, cosecant, cotangent of theta. So we could make a reference triangle in terms of the angle theta based off our substitution, But here, our answer involves sine of twice the angle theta. So in order to get our answer in terms of trig functions involving just theta, we can use a double angle identity for sine, which says that sine of 2 theta is equal to 2 times sine theta cosine theta. So a little note at the top here, I'm using the fact that sine of 2 times theta is equal to 2 sine theta cosine theta. So making that simplification, well, I see that a factor of 1/2 and 2 cancel. So I'm left with 8 theta plus 8 sine theta cosine theta plus c. And now I can move back to an answer in terms of x. So let's see what we have. I have my constant 8 times theta. Now looking back at our substitution, x was equal to 4 sine theta. So sine of theta is x over 4. In solving for theta, well, I would take the arcsine or sine inverse of that ratio, x over 4. Then we have plus 8 times sine of theta, which we just said is x over 4 using our substitution, times cosine of theta. Now, if I look back at my earlier work, I have this equation involving cosine of theta. So to solve for cosine theta, in terms of x, I could just divide this equation through by 4, and I'm left with the square root of 16 minus x squared over 4. And then I've got my plus c on the end. So simplifying a little bit, I've got 8 times arcsine of x over 4, plus, grouping our constant terms, well, we have 8 divided by 4 times 4 is 16. So 8 over 16 is 1/2 of, we had an x times the square root of 16 minus x squared plus c. All right.